I've been thinking a lot about infinity, and specifically about whether the universe itself might be infinite. And it's one of those questions that when you first hear it seems almost impossible to even approach, right? I mean, how do you wrap your mind around something that goes on forever? But the strange thing is, the more you dig into this question, the more you realize that infinity isn't just some abstract mathematical concept that philosophers argue about over coffee. It's actually a real physical possibility for the cosmos we inhabit. And that's both beautiful and deeply unsettling in ways that are hard to articulate. Let me start with something simple, something we can all relate to. When you look up at the night sky, when you see all those stars scattered across the darkness, what are you really seeing? You're seeing light that's traveled for years, sometimes millions or billions of years. To reach your eyes, you're looking backward in time, essentially, because light has a speed limit, and that means everything we observe is how it was when the light left it, not how it is now. And that's just the beginning of the strangeness, because what you're seeing, all those stars and galaxies, that's just a tiny, infinitesimally small fraction of what's out there. The observable universe, the part we can actually see, is like a sphere around us with a radius of about 46 billion light years. That's huge, almost incomprehensibly huge. But here's the thing, here's what keeps cosmologists up at night. That might just be a tiny bubble, a microscopic speck, in something far, far larger. The universe beyond what we can see, well, it might go on forever. And when I say forever, I mean actually infinite. Not just really big, not just bigger than we can imagine, but genuinely without end. No edge, no boundary, no point where you'd hit some cosmic wall with a sign saying end of universe, turn back. Just more space, more galaxies, more stars, extending outward in all directions without ever stopping. It's hard to picture, isn't it? Because our brains didn't evolve to understand infinity. We evolved to understand the sizes of things we could see and touch, things that had edges and boundaries. The idea of something that just keeps going, that never ends no matter how far you travel, that's not something our intuition knows how to handle. But here's where it gets interesting, where the science starts to tell us something profound about reality. You see, for most of human history, people didn't think the universe was infinite. They thought it was big, sure, but finite, bounded. The ancient Greeks, brilliant as they were, imagined the cosmos as a series of nested spheres with Earth at the center and the stars embedded in the outermost sphere. It was beautiful, geometric, comprehensible. Medieval thinkers inherited this view and elaborated on it, creating these intricate models where everything had its place, its proper sphere, its distance from the center. And in these models, the universe had a size. You could, in principle, measure it. It wasn't infinite. Even when Copernicus came along and moved the sun to the center, even when Galileo pointed his telescope at the heavens and saw moons orbiting Jupiter and realized that Earth wasn't special, the universe was still thought to be bounded. Large, yes, larger than anyone had imagined, but not infinite. There was still this sense that if you traveled far enough, you'd reach some kind of edge, some boundary between existence and non-existence. And that makes sense, right? It's comforting in a way to think that the universe has limits, that it's contained, that it's something we could, in principle, map completely if we just had enough time and good enough telescopes. But then Einstein came along and everything changed. I mean, everything. Einstein's general theory of relativity, published in 1915, revolutionized how we think about space and time and gravity. And one of the things it did, one of the most profound things, was to give us a framework for understanding the universe as a whole, for treating the entire cosmos as a single unified object that we could study scientifically. Before Einstein, the question, what is the shape and size of the universe, wasn't really a scientific question. It was more philosophy, more metaphysics. But general relativity made it physics. It gave us equations, mathematical tools, ways to model the entire universe and make predictions about it. And here's what's remarkable about those equations. They don't prefer a finite universe. They don't say the universe must have edges. In fact, depending on certain properties of the universe, properties we can actually measure, the equations tell us that the universe could be infinite. Not might be, not probably is, but actually could be, as a genuine physical possibility consistent with everything we know about physics. That's a big deal, because it means infinity isn't just a mathematical curiosity or a philosophical puzzle. It's a real option for the nature of reality. Let me explain how this works because it's not immediately obvious. General relativity tells us that the geometry of space itself, the way distances work, the way parallel lines behave, all of that depends on the distribution of matter and energy in the universe. Mass and energy curve space-time, right? That's the famous insight. The sun curves the space around it, and Earth follows that curve, and we call that curved path an orbit. But what Einstein and others realized was that you could apply this same logic to the entire universe. All the matter and energy in the cosmos taken together determines the overall geometry of space itself. And there are, broadly speaking, three possibilities for this geometry, three shapes the universe could have. Think of it like surfaces because that's the easiest way to visualize it, even though we're really talking about three-dimensional space having different geometric properties. The universe could be positively curved like the surface of a sphere. It could be negatively curved like a saddle shape, or it could be flat like a sheet of paper extending in all directions. And here's the crucial part. If the universe is positively curved like a sphere, then it's probably finite. Not definitely, because there are some exotic topological possibilities, but probably. It would be like living on the surface of a giant balloon, where if you traveled far enough in one direction, you'd eventually come back to where you started. No edge, but still finite, still bounded in total size. But if the universe is flat, or if it's negatively curved like a saddle, well, then it's most likely infinite. It just goes on forever, extending outward without end in all directions. And the thing is, we can actually measure which of these is true. We can determine the geometry of the universe by looking at how things are distributed in space, by measuring angles and distances, and seeing if they obey the rules of flat geometry or curved geometry. And when cosmologists have done these measurements, when they've looked at the cosmic microwave background radiation and the distribution of galaxies and all the other data we have, what they've found is that the universe appears to be flat, or at least it's so close to flat that we can't detect any curvature with our current instruments. Now, that doesn't prove the universe is infinite. It's possible, technically possible, that the universe is positively curved, but the curvature is so slight that we can't measure it yet. It's possible that we live in a finite but absolutely enormous cosmos where the curvature is there but stretched out over such vast distances that it looks flat to us. That's like how the Earth looks flat when you're standing on the surface, even though it's actually a sphere. If you were an ant on a basketball, the surface would look flat to you too. So we can't say with absolute certainty that the universe is infinite. But here's the thing. If the universe is flat, as the measurements suggest, then the simplest explanation, the most straightforward interpretation of the equations is that it's infinite. Not just really big, actually infinite. And that means there are infinite galaxies, infinite stars, infinite planets. It means that everything that can happen does happen somewhere out there in the infinite expanse. It means that there are, quite literally, infinite versions of every possible arrangement of matter and energy, repeating over and over again at different scales and in different locations throughout the cosmos. And that's where things start to get philosophically strange, because infinity has these weird properties. If the universe is truly infinite, and if it's roughly uniform in its properties, which is what we observe in the parts we can see, then that uniformity has to extend everywhere. And that means that at some vast distance, far beyond what we could ever observe, there's another region of space that looks exactly like our region. Same galaxies, same stars, same planets. And farther out, there's another one, and another. An infinite number of them, actually, because in an infinite universe with finite possibilities at any given scale, everything that can happen must happen infinitely many times. That sounds crazy, right? It sounds like science fiction. But it's actually a direct logical consequence of infinity combined with uniformity. Think about it this way. If you shuffle a deck of cards infinitely many times, every possible arrangement will come up infinitely many times. You can't avoid it. The possibilities are finite, the shuffles are infinite, so repetition is inevitable. The same logic applies to the universe. There are only so many ways to arrange atoms in a region of space the size of, say, the observable universe. It's a huge number, incomprehensibly huge, but it's finite. And if space is infinite, then every one of those arrangements exists somewhere, and in fact exists infinitely many times, scattered throughout the endless expanse. But let's step back for a moment, because I'm getting ahead of myself. I want to talk about how we actually know anything about the universe's geometry, about how we can measure something so vast and fundamental. And the key to understanding this is the cosmic microwave background radiation, which is, I think, one of the most beautiful and important discoveries in all of science. You see, the universe hasn't always been the way it is now. We know this because we can see the universe changing. When we look at distant galaxies, we see them moving away from us. The farther away they are, the faster they're receding. And this isn't because they're moving through space exactly. It's because space itself is expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread. And if the universe is expanding now, that means it was smaller in the past. And if you run the clock backward, if you extrapolate that expansion in reverse, you eventually reach a point where everything was compressed into an incredibly hot, incredibly dense state. That's the Big Bang, the beginning of the universe as we know it. But here's what's crucial. The Big Bang wasn't an explosion in space. It was the beginning of space itself. Time, space, matter, energy, all of it emerged from this initial state about 13.8 billion years ago. And in those first moments, the universe was so hot and so dense that atoms couldn't even form. It was just this seething plasma of particles and radiation, opaque to light, glowing with incredible intensity. But then, as the universe expanded and cooled, there came a moment, about 380,000 years after the Big Bang, when the temperature dropped enough for electrons to combine with protons and form hydrogen atoms. And suddenly, for the first time, the universe became transparent. Light could travel freely through space without being scattered by free electrons. That light, the light that was released at that moment of transparency, is still traveling through the universe today. It's been stretched and redshifted by the expansion of space, cooled from thousands of degrees down to just a few degrees above absolute zero, but it's still here, filling all of space with this faint glow. We call it the cosmic microwave background radiation, and we can detect it with radio telescopes, mapping it out in exquisite detail across the entire sky. And what that map tells us, what we see when we look at the patterns in that ancient light, is information about the geometry and composition of the universe. The cosmic microwave background has these tiny fluctuations in temperature, little hot and cold spots that correspond to slight density variations in the early universe. And the size and pattern of those fluctuations depends on the geometry of space. If the universe is positively curved like a sphere, the spots would appear larger than they would in a flat universe. If it's negatively curved, they'd appear smaller. So by measuring the angular size of these fluctuations with incredible precision, cosmologists can determine the curvature of the universe. And what they've found, what the data shows, is that the universe is flat to within about 1% accuracy, which means either it's exactly flat, which would imply it's infinite, or it has such slight curvature that the total size must be at least hundreds of times larger than the observable universe. Either way, it's vastly larger than what we can see, and quite possibly infinite. But there's another piece to this puzzle, another reason to think the universe might be infinite, and it has to do with a theory called cosmic inflation. Now, inflation is this idea that in the very earliest moments of the universe, in the first tiny fraction of a second after the Big Bang, space expanded exponentially fast, faster than the speed of light, doubling in size over and over again in an incredibly short time. And this inflation, this rapid expansion, solved several puzzles that cosmologists had been struggling with. It explained why the universe is so uniform, why it looks the same in all directions. It explained why the geometry is so close to flat. And it explained certain features of the cosmic microwave background that didn't make sense in the standard Big Bang model. But here's where it gets really interesting, where the implications become profound. You see, in most versions of inflation theory, once inflation starts, it doesn't necessarily stop everywhere at once. Different regions of space can stop inflating at different times. And in some versions of the theory, in what's called eternal inflation, there are regions that never stop inflating. They just keep expanding forever. And within that eternally inflating space, little pocket universes like ours bubble off like bubbles forming in boiling water. Each pocket universe stops inflating locally and goes through its own Big Bang, its own expansion and cooling, its own evolution into galaxies and stars and planets. And if that's true, if eternal inflation is the correct picture, then our universe, the entire vast expanse that we can see, and even the infinite space beyond it that we can't see, might just be one bubble in an infinite foam of universes. The multiverse, they call it. And each of those universes might have different properties, different physical constants, different laws of physics even. Some might be hospitable to life, most probably aren't. But if there are infinitely many of them, then every possibility gets realized somewhere. Now, I should be clear about something here. The multiverse is speculative. It's not proven. It's a prediction of certain theories, particularly eternal inflation, but we don't have direct evidence for it, and it's not clear we ever could, because by definition, these other universes would be causally disconnected from ours. We couldn't see them or visit them or interact with them in any way. So some physicists love the multiverse idea, think it's the natural consequence of our best theories. Others hate it, think it's untestable metaphysics masquerading as science. It's genuinely controversial. But here's what's not controversial. Even if we just stick to our own universe, even if we ignore the multiverse entirely, the universe we inhabit is either infinite or so staggeringly huge that the distinction barely matters. And that raises all these profound questions about what infinity means, about what it implies for existence and identity and possibility. Think about it this way. If the universe is infinite, and if it's roughly uniform in its properties, then somewhere out there, impossibly far away, there's another Earth. Not similar to Earth, exactly like Earth, atom for atom. And on that Earth, there's another you, living another version of your life, maybe making the same choices you're making, maybe making different ones. And there's not just one such copy. There are infinitely many. Some very similar to you, some radically different. Some where you chose a different career, where you moved to a different city, where you never met certain people or met different people. Every possible variation exists somewhere in the infinite expanse. And that's hard to process, isn't it? Because it challenges our sense of uniqueness, our feeling that we're special, that our choices matter in some fundamental way. If there are infinite versions of me making every possible choice, does any individual choice really matter? Or am I just one of countless copies, no more significant than any other? These are the kinds of questions that keep philosophers up at night, and they're raised not by fantasy or speculation, but by the straightforward physical possibility that the universe is infinite. But let me pull back again, because I want to make sure we understand what we mean when we talk about the universe being infinite. There are actually different ways space could be infinite, different topologies and geometries that all count as infinite but have different properties. The simplest version, the one I've mostly been talking about, is just flat Euclidean space extending forever in all directions. That's infinite in the most straightforward sense. You could travel in any direction forever and never hit an edge, never loop back to where you started. But there are other possibilities. Space could be flat, but have a weird topology, like a torus or a Klein bottle. Imagine a video game where when you go off the right edge of the screen, you reappear on the left edge. The screen itself is finite, but the space is wrapped around on itself, so there's no boundary. You could travel forever and never hit an edge, but you'd eventually come back to where you started, seeing the same structures again and again. That's finite in volume, but unbounded, infinite in the sense that you could travel along any path forever. It's topologically weird, and there's no strong evidence that our universe has this kind of topology, but it's possible. Or space could be negatively curved, like a saddle shape extended to 3 dimensions. That's called hyperbolic geometry, and in that case, space is definitely infinite. Parallel lines diverge, triangles have angles that add up to less than 180 degrees, and volume grows exponentially with distance. A negatively curved universe would be infinite and would have this strange property where there's actually more room, more volume than you'd expect from the distances involved. It would be, in some sense, even more spacious than flat infinite space. The point is, infinity comes in different flavors, and we need to be careful about what we mean when we ask if the universe is infinite. Are we asking about spatial extent, about whether you could travel forever, about the total volume of space, about whether the universe has an edge or boundary? These are related questions, but they're not identical, and the answers depend on both the geometry and the topology of space. And here's another subtlety, another layer to this. When we talk about the universe being infinite, we usually mean infinite in space. But what about time? Did the universe have a beginning, or has it existed forever? Will it have an end, or will it go on forever? These are separate questions from whether space is infinite, and the answers aren't necessarily the same. Most cosmologists think the universe did have a beginning, the Big Bang, about 13.8 billion years ago. That's when time itself began, at least according to the Standard Model. But some theories suggest the Big Bang might not have been the absolute beginning. Maybe it was just a transition from some previous state. Maybe there was a pre-Big Bang universe that collapsed and then rebounded. Or maybe time is eternal, stretching infinitely far into the past and future, with the Big Bang being just a particularly dramatic event in an eternal history. We don't know. The physics of those earliest moments, the Planck era when quantum effects and gravity were both incredibly strong, is something we don't understand yet. We don't have a theory of quantum gravity that we trust, and without that, we can't say for sure what happened at the very beginning, or if there even was a beginning, in the sense we usually mean. And then there's the future. Will the universe go on forever? Well, that depends on dark energy, this mysterious component of the universe that seems to be causing the expansion to accelerate. We don't know what dark energy is. We can measure its effects, we can see that the expansion of the universe is speeding up rather than slowing down, but we don't understand the underlying cause. Is it a cosmological constant, a property of empty space itself? Is it some kind of field or energy that's filling the universe? Is it a sign that our understanding of gravity breaks down on cosmic scales? We don't know. But if dark energy continues to dominate, if the acceleration continues, then the universe will expand forever, faster and faster, until eventually even galaxies that are relatively close to us now will be moving away so fast that their light can never reach us. The observable universe will shrink, in a sense, even though space itself keeps expanding. In the far future, in trillions of years, any civilization in our galaxy would look out and see nothing but darkness. All the other galaxies would have receded beyond the cosmic horizon, their light stretched to infinite wavelengths, effectively disappearing from view. And eventually, even stars will burn out. Black holes will evaporate through Hawking radiation, and the universe will become this cold, dark, empty expanse, approaching thermodynamic equilibrium. Heat death, they call it. The end of everything interesting, the final state where nothing can happen anymore because there's no energy gradient to drive processes. That's one scenario. But there are others. Maybe dark energy isn't constant. Maybe it changes over time, or maybe it's not really dark energy at all, but a sign that we need to modify general relativity. In that case, the universe's fate could be different. It might recollapse in a big crunch, or it might tear itself apart in a big rip where the acceleration becomes so extreme that eventually atoms and even particles get ripped apart. Or something else entirely might happen, something we can't predict because we don't understand the underlying physics. The point is, when we talk about infinity, we need to be clear about what kind of infinity we mean. Spatial infinity is one thing, temporal infinity is another, and they don't necessarily go together. The universe could be spatially infinite but temporally finite, or spatially finite but temporally infinite, or both finite or both infinite. The geometry of space and the evolution of the universe in time are related but distinct questions. Now, let me talk about something else, something that's been bothering me throughout this whole discussion, which is the relationship between the observable universe and the universe as a whole. Because when we say the universe might be infinite, we're making a claim that goes way, way beyond anything we can actually observe. The observable universe, remember, has a finite size. It's huge, about 93 billion light years across, but it's finite. That's because light has only had a finite amount of time to reach us since the Big Bang. Light travels at a finite speed and the universe has a finite age, so there's a limit to how far we can see. Anything beyond that limit, its light simply hasn't had time to reach us yet. And with the expansion of space, there are regions that we will never be able to observe no matter how long we wait, because they're receding from us faster than light can travel through space. So when we say the universe is infinite or might be infinite, we're extrapolating beyond what we can see. We're assuming that the properties we observe in the local universe, the homogeneity, the isotropy, the flat geometry, continue to hold far beyond the observable region. And that's a reasonable assumption based on the cosmological principle. This idea that the universe looks the same everywhere and in all directions on large scales, but it is an assumption. We can't prove it. We can't check it by observation. because by definition we can't observe those distant regions. And that raises a fascinating question. If we can never observe these distant regions, if they're forever beyond our cosmic horizon, can we really say they exist? Is it meaningful to talk about parts of the universe that we can never see, never interact with, never obtain any information about? This gets into deep philosophical territory, into questions about what existence means, what reality is. Some physicists would say yes, absolutely those regions exist, just as much as the parts we can see exist. The laws of physics don't stop at the edge of the observable universe. Space continues, time continues, galaxies and stars continue to form and evolve, whether we can see them or not. Reality is what it is, independent of our ability to observe it. But other physicists, particularly those influenced by quantum mechanics and its interpretations, might be more cautious. They might say that talking about things we can never in principle observe is metaphysics, not physics. That science deals with what we can measure and test, and anything beyond that is speculation. And while we can extrapolate using our theories, we should be humble about those extrapolations, recognizing that they're based on assumptions that might not hold in regions we can't check. I tend to lean toward the first view, the realist view, that the universe exists independent of our observations of it. But I respect the second view too, and I think it's important to acknowledge the limits of what we can know. The universe might be infinite, and I think it probably is, or at least it's so vast that the distinction doesn't matter practically. But we can't be absolutely certain, because absolute certainty would require observing the entire universe, and that's impossible if it's infinite. Let me shift gears and talk about one more aspect of this, which is how infinity interacts with quantum mechanics. Because quantum mechanics has its own brand of infinity, its own way of making things weird, and when you combine quantum mechanics with cosmology, you get some truly mind-bending ideas. In quantum mechanics, particles don't have definite properties until they're measured. They exist in superpositions, multiple states at once, described by wave functions that give probabilities for different outcomes. And there's this famous problem, the measurement problem, of how and why the wave function collapses to give a definite outcome when we make a measurement. Different interpretations of quantum mechanics handle this differently. Some say the wave function really does collapse instantaneously when measured. Others say there's no collapse at all, that all the possible outcomes actually happen, splitting into different branches or worlds. That's the many worlds interpretation, and it's popular among cosmologists because it avoids the measurement problem by saying there's no collapse. Every quantum event, every moment where particles could go one way or another, the universe splits, or rather, was always going to split, into branches where each outcome occurs. And if that's true, if many worlds is correct, then even in a finite universe, there would be an effectively infinite number of parallel branches, all equally real, all coexisting in some abstract quantum state space. But now combine that with an infinite universe. If space is infinite and quantum mechanics is fundamentally about probabilities and multiple outcomes, then you get this picture where not only is there infinite space with infinite possibilities realized, but each point in that infinite space is constantly branching into infinite quantum worlds. It's infinity upon infinity, layers of endlessness stacked on top of each other. And that's almost impossible to wrap your mind around. Some physicists have tried to calculate how far you'd need to go in an infinite universe before you found a region identical to ours, taking quantum mechanics into account. And the numbers are stupendous, so large they're meaningless in any practical sense. But the point is, in an infinite universe with quantum branching, everything that's possible, every quantum outcome, every arrangement of matter, all of it exists somewhere, somehow, in the vast ensemble of possibilities. And that leads to this idea, this unsettling but fascinating idea, that in an infinite universe you're not unique. You're one instance of a pattern that repeats infinitely many times. And not just you as you are now, but every version of you that could have been, given different quantum outcomes at critical moments in your past. Every decision you made, there are versions of you who made the opposite decision. Every accident you avoided, there are versions of you who didn't avoid it. Every opportunity you missed, there are versions of you who took it. All of them exist scattered throughout the infinite expanse, or branching through the infinite tree of quantum worlds, or both. That's a lot to take in, you know. It challenges our sense of identity, our feeling that we're singular individuals with unique histories and futures. If there are infinite copies of me, what makes this particular version special? What makes my choices meaningful if there are other versions making every possible choice? These are profound questions, and they don't have easy answers. Some people find this view liberating, this idea that all possibilities are realized somewhere. Others find it disturbing, even nihilistic. I think it's mostly just strange, one of those things where reality turns out to be weirder than we could have imagined. But let me bring things back to earth, so to speak, and talk about why any of this matters. Why should we care whether the universe is infinite? What difference does it make to our lives, to our understanding of ourselves and our place in the cosmos? Well, for one thing, it affects how we think about probability and fine-tuning. There's this puzzle in cosmology and physics about why the universe seems so finely tuned for life. The physical constants, the strength of forces, the properties of particles, if any of them were even slightly different, stars wouldn't form, or atoms wouldn't be stable, or chemistry would be impossible, and life as we know it couldn't exist. Some people look at this fine-tuning and see evidence of design, of some intelligent creator who set the constants just right. Others see it as a mystery that needs explanation. But if the universe is infinite, and especially if there's a multiverse with different properties in different regions, then the fine-tuning problem goes away, in a sense, because if there are infinite regions with different properties, then some of them, by sheer chance, will have the right properties for life. And of course, we find ourselves in one of those regions because we couldn't exist in the others. It's an observer selection effect, the anthropic principle. We observe a life-friendly universe, not because the universe was designed for life, but because we couldn't observe any other kind. If the universe weren't suitable for life, we wouldn't be here to wonder about it. Now, not everyone finds this satisfying. Some people think the anthropic principle is a cop-out, a way of avoiding the real question of why the constants have the values they do. And they might be right. Maybe there's a deeper theory, a theory of everything, that predicts the values of the constants from first principles, making the fine-tuning question moot. We don't know yet. But the point is, infinity and the multiverse change how we think about these questions. They expand the space of possibilities, making what seems improbable in one universe inevitable across infinite universes. And there's something else, something more personal and existential. The idea of an infinite universe challenges us to think about meaning and significance in a new way. If the universe is finite, if it's bounded, then there's a sense in which we can imagine understanding it completely, mapping it all, knowing everything there is to know. It's a comforting thought, the idea that reality is, in principle, comprehensible, containable within our minds or our theories. But if the universe is infinite, then that dream of complete understanding is impossible. There's always more, always further to go, always deeper levels of complexity and structure. We can never know everything because there's literally infinite things to know. And maybe that's okay, maybe that's even beautiful, because it means the universe never stops being interesting, never stops offering new mysteries to explore, new questions to ask. An infinite universe is a universe that will always surprise us, always challenge us, always invite us deeper into understanding. And there's something profoundly hopeful about that, I think. It means our quest for knowledge is never ending, not because we're slow or limited, but because reality itself is inexhaustible. There's also this question of how we should feel about our place in an infinite cosmos. Are we insignificant, just one tiny speck in an endless expanse? Or are we special precisely because we're conscious beings who can comprehend or try to comprehend the vastness of it all? I tend to think both are true. We're cosmically insignificant in terms of size and duration. The universe doesn't care about us, doesn't know we exist, will continue long after we're gone. But we're also remarkable, maybe even miraculous, because we're the part of the universe that's become aware of itself, that can look outward and inward and ask these profound questions about existence and meaning. And in an infinite universe, that kind of awareness, that consciousness, must exist in infinite forms, infinite times, infinite places. We're not alone in that sense. Somewhere out there, infinitely far away, there are other beings looking up at their night sky, asking the same questions, feeling the same sense of wonder and confusion and curiosity that we feel. We'll never meet them, never communicate with them, because the distances are too vast and the speed of light is too slow. But they're there if the universe is infinite. And somehow, knowing that, even just as an abstract possibility, makes the universe feel less cold, less empty. But I want to come back to the science for a moment because there are some practical, observational questions about infinity that we can actually address. One of them has to do with whether the universe has enough matter and energy to close it, to make it finite. You see, the geometry of space depends on the density of matter and energy. If the density is exactly at a critical value, space is flat. If it's higher than that critical density, space is positively curved and finite. If it's lower, space is negatively curved and infinite. And we can measure the density, we can count up all the matter and energy in the universe and see how it compares to that critical value. And what we've found is that the universe is incredibly close to that critical density, so close that it's flat within observational error. But that raises this puzzle. Why is the density so close to critical? If you start with almost any initial conditions and let the universe evolve, the density should diverge from the critical value over time. A slightly higher density becomes much higher. A slightly lower density becomes much lower. But we observe it right at the critical value, even though billions of years have passed since the Big Bang. That's the flatness problem. And the answer, or at least the proposed answer, is inflation. During the inflationary epoch, space expanded so rapidly, doubled in size so many times, that any initial curvature was stretched out, flattened, just like inflating a balloon makes its surface look flatter at any small region. So inflation predicts that the universe should be extremely flat, almost exactly at the critical density. And that's what we observe. The flatness is evidence for inflation. But here's the thing. If inflation drove the density to exactly the critical value, then the universe is flat. Not just approximately flat, but exactly flat. And if it's exactly flat, then it's infinite. Not finite but large, not curved but undetectably so, but truly infinite, extending forever in all directions. That's a direct consequence of the most straightforward interpretation of inflation combined with our observations. Now, there are caveats. Maybe the universe is so large that we can't detect the curvature yet, but it's there. Maybe future, more precise measurements will reveal a slight positive curvature indicating a finite universe. That's possible. But right now, with the data we have, the simplest interpretation is that the universe is flat and therefore infinite. And there's another line of evidence, another way to think about this, which has to do with the large-scale structure of the universe. When we map out galaxies, when we look at how they're distributed in space, we see this pattern, this cosmic web of filaments and voids, with galaxies clustered along the filaments and vast empty spaces in between. And the pattern looks the same, no matter where you look or how far out you go. It's statistically uniform, homogeneous on large scales. Every region looks like every other region on average. And if that homogeneity extends beyond the observable universe, if the pattern continues indefinitely, then that's consistent with an infinite universe. Because why would the pattern stop at the edge of what we can see? There's no reason, no mechanism for the universe to be fundamentally different just beyond our cosmic horizon. The laws of physics don't change out there. Gravity still works the same way. Matter still clumps and forms galaxies and stars. So the most natural assumption is that what we see here continues everywhere, extending outward without end. Of course, we can't prove this. We can't observe those distant regions to check. But Occam's razor, the principle of parsimony, suggests that we shouldn't multiply entities without necessity, shouldn't assume complexity without evidence. And the simplest assumption is that the universe is the same everywhere, that what we observe locally is representative of the whole. And if that's true, if the universe is homogeneous and flat, then it's infinite. Let me talk about one more thing, one more aspect of infinity that's worth considering, which is how it relates to the beginning of the universe. Because if space is infinite now, and if the universe has been expanding since the Big Bang, does that mean space was infinite at the beginning too? And if so, how do you get an infinite universe from a Big Bang? This is a subtle question, and the answer is a bit counterintuitive. Yes, if the universe is infinite now, it was infinite at the Big Bang too, but it was also infinitely dense at the Big Bang. or at least approached infinite density as you go back toward the initial moment. How can that be? How can something be both infinite in extent and infinite in density? Well, the key is that the Big Bang wasn't an explosion at a point. It wasn't a localized event that happened somewhere and then expanded outward. It was an event that happened everywhere, at every point in space, all at once. Space itself was expanding, carrying matter and energy along with it, but there was no center, no edge, no boundary. If space is infinite, then it was infinite at the Big Bang. But the distance between any 2 points was smaller, approaching zero as you go back to the initial moment. Think of it like this. Imagine an infinite grid of points, extending forever in all directions. Now imagine shrinking all the distances between the points by a factor of 2. The grid is still infinite, still has infinitely many points, but they're closer together. Shrink by a factor of 2 again, and again, infinitely many times. In the limit, the distance between any 2 points approaches zero, but there are still infinitely many points. And the space is still infinite in extent. That's kind of what the Big Bang was like, except with 3-dimensional space instead of a 2-dimensional grid. So an infinite universe doesn't have a problem with the Big Bang. It just means the Big Bang was an infinite event, happening everywhere at once, rather than a localized explosion. And that actually solves some puzzles, like why the universe is so uniform. If the Big Bang happened everywhere, then every region of the universe had the same starting conditions, went through the same evolution, and ended up looking similar. There's no mystery about why distant regions look like nearby regions, because they all came from the same initial state. But there's still this question, this deep question of why there was a Big Bang at all. Why does the universe exist? Why is there something rather than nothing? And infinity doesn't really help with that question. An infinite universe is just as mysterious, just as in need of explanation, as a finite one. Maybe more so because infinity itself is such a strange concept, so difficult to grasp. Why should reality be infinite? What does that even mean? And here's where we reach the limits of science, the boundary between physics and metaphysics. Science can tell us how the universe works, what laws govern it, how it's evolved and how it will evolve. But science can't, or at least hasn't yet, told us why there's a universe at all, why anything exists, why the laws are what they are instead of something else or nothing at all. Those are philosophical questions, maybe even theological questions, and they don't have clear answers. Some physicists have proposed that the universe came from nothing, from quantum vacuum fluctuations, that it's a sort of accident of quantum mechanics. Others think that's nonsense, that you can't get something from nothing, that there must be some deeper explanation. Still others think the question itself is malformed, that asking what came before the Big Bang is like asking what's north of the North Pole. Time began at the Big Bang, in this view, so there is no before, and the question doesn't make sense. I don't know which of these views is correct. I'm not sure anyone does. But what I do know is that the universe, whether finite or infinite, is strange and beautiful and worthy of our wonder. We live in a cosmos that's vast beyond comprehension, ancient beyond imagining, intricate in its structure and laws. And we're part of it, made of the same stuff as stars, subject to the same forces, governed by the same principles. We're not separate from the universe, looking at it from outside. We're inside it, of it, continuous with it. And if the universe is infinite, then that continuity extends forever. There's no boundary between us and the cosmos, no edge where we stop and something else begins. We're expressions of the universe's complexity, local concentrations of order and consciousness in a vast sea of space and energy. And that's remarkable, that's something to feel grateful for, even in the face of our cosmic insignificance. Because significance isn't about size or duration, it's about meaning, about value, about the quality of experience and thought and feeling, and consciousness, awareness, the ability to ask these questions and marvel at the answers. That's significant in the deepest sense, regardless of how much space it occupies or how long it lasts. So where does this leave us? What can we conclude about whether the universe is infinite? Well, we can say that it might be. The evidence suggests it's flat or very close to flat, which in the simplest models means it's infinite. The theory of inflation predicts that it should be flat, which supports the infinite interpretation. The homogeneity and isotropy we observe don't require infinity, but they're consistent with it. and would naturally extend beyond the observable region if the universe is infinite. But we can't be certain. We can't observe the entire universe to check. We can't rule out the possibility that it's finite but so large that we can't detect the curvature. We can't rule out exotic topologies that make space finite but unbounded. We can't even be certain that our fundamental theories are correct at the scales and energies where these questions become crucial. What we can say is that the universe is far larger and stranger than humans imagined for most of history, that the observable universe, vast as it is, might be just a tiny fraction of the whole. That reality might extend forever, infinite in space, infinite in time, infinite in possibilities, and that even if it doesn't, even if the universe is finite, it's still so enormous and so old and so complex that we'll never run out of things to discover, questions to ask, mysteries to ponder, and maybe that's the most important thing. Not whether the universe is technically infinite or just incomprehensibly large, but that it's bigger than us, older than us, stranger than us, and yet also comprehensible to us, at least in part, through science and reason and observation. We can look outward and understand, even if we can't see everything. We can formulate theories and test them, build models and refine them, ask questions and find answers. And in that process, in that ongoing conversation between us and the cosmos, we find meaning and purpose and wonder. The universe might be infinite, probably is infinite, if I had to guess, based on the current evidence and the simplest interpretation of our best theories. But even if it's not, even if it's finite, it's still far beyond anything we can fully grasp or explore or understand. And that's okay. That's more than okay. Because the journey of understanding, the quest to learn and discover and comprehend, that's what makes us human. That's what gives our lives depth and richness and significance. And in an infinite universe, or even just a very large, finite one, that quest never ends. There's always more to learn, always further to go, always deeper to dive. And that's beautiful, I think. That's something to celebrate, because it means we'll never be bored, never run out of questions, never exhaust the mystery of existence. The universe, whether infinite or not, is an endless source of wonder, and we're privileged to be here, to be part of it, to be the part that looks back at itself and asks, why? How? What does it all mean? Those questions don't have final answers. Maybe they can't have final answers. But asking them, exploring them, living them, that's what it means to be conscious beings in a vast and ancient cosmos. And whether that cosmos goes on forever or eventually ends, whether it's infinite or merely enormous, the asking is what matters. The wondering is what makes us who we are. And as long as there are minds to wonder, as long as there are eyes to look up at the night sky and feel that sense of awe and curiosity, the universe will be, in the most important sense, alive. Aware of itself through us, thinking about itself through our thoughts, marveling at itself through our wonder. And that's the answer, if there is one, to why the universe might be infinite. Not because we can prove it with certainty, not because the equations demand it, though they might, but because infinity captures something essential about existence itself, about the endless creativity of reality, the inexhaustible depth of what is. An infinite universe is a universe that never stops giving, never stops surprising, never stops inviting us deeper into understanding. And even if the universe isn't infinite, even if it has an edge or a boundary or an end, it feels infinite. It presents us with infinite questions, infinite puzzles, infinite opportunities for discovery. And so we keep looking, keep asking, keep wondering. We point our telescopes at the sky and our equations at the cosmos. We build theories and test them, measure distances and count galaxies, map the cosmic microwave background and calculate curvatures. We push the boundaries of what we know, always reaching for what we don't yet understand. And in that reaching, in that endless striving toward knowledge, we find something like transcendence, not religious transcendence necessarily, though some might frame it that way, but intellectual transcendence, the ability to step outside ourselves, outside our limited perspective, and glimpse the bigger picture. The universe might be infinite. And we, tiny and brief as we are, can understand that possibility, can grapple with it, model it, discuss it, wonder about it. And that's extraordinary. That's the real miracle, if you want to call it that. Not that the universe is big, but that we can comprehend its bigness. Not that it's ancient, but that we can trace its history. Not that it's complex, but that we can decipher its patterns and principles. So yes, the universe might be infinite. The evidence points that way, the theories suggest it, the logic supports it, but whether it is or isn't, the truly amazing thing is that we can ask the question at all, that we can look out into the darkness, past the stars, past the galaxies, past the edge of everything we can see, and wonder what lies beyond, and then use math and physics and reason to actually answer that question, or get close to an answer, or at least narrow down the possibilities. That's the human project. That's what we do. We ask impossible questions and then find ways to answer them. We look at the universe and don't just see pretty lights, but see distance and time and motion and structure. We don't just wonder, we understand. And infinity, that most impossible of concepts, that idea that seems to defy comprehension, we can grasp it. Maybe not fully, maybe not perfectly, but enough. Enough to ask if the universe is infinite, enough to design experiments and observations that might tell us the answer, enough to know that we don't yet know for certain, but we're getting closer. And that's where I want to leave this, with that sense of ongoing discovery of questions asked and partially answered, of mysteries explored but not exhausted. The universe might be infinite, extending forever in all directions, filled with infinite galaxies and infinite stars and infinite possibilities. Or it might be finite, bounded in some way we don't yet understand, limited, but still vast beyond our ability to fully explore. Either way, it's magnificent. Either way, it's more than enough to keep us wondering for as long as our species exists, and probably far longer. The universe doesn't owe us answers. It doesn't owe us anything. It simply is, indifferent to our existence, uncaring about our questions. But we ask anyway. We wonder anyway. We reach out with our minds and our instruments and our theories, trying to understand, trying to know, trying to see the full picture, even though we can only ever see a part of it. And in that trying, in that reaching, we find meaning, we create significance where none existed before. We take a universe that doesn't care and make it matter to us because we care. And if the universe is infinite, then somewhere out there, impossibly far away, other beings are doing the same thing, asking their own questions, building their own theories, wondering about their own existence and their place in the cosmos. We'll never meet them, never speak to them, never even know they exist. But if infinity is real, they're there. And that's a comforting thought in its own strange way. We're not alone in our wondering, even if we're alone in our corner of space. The cosmos is filled, perhaps infinitely filled, with consciousness and curiosity and the drive to understand. And that might be the best answer to the question of meaning in an infinite universe. The meaning is in the asking, the significance is in the search, and the beauty is in the wonder we feel when we look up at the night sky and really realize how vast it all is, how ancient, how strange, how magnificent. Infinite or not, the universe is extraordinary. And so are we, for being able to comprehend even a fraction of its extraordinariness. Now let's move on to another theory for you to reflect on. I've been thinking a lot about black holes lately, and the more I think about them, the more I realize they're not what most people imagine them to be. When you hear black hole, what comes to mind? Probably something like a cosmic vacuum cleaner, right? This thing out in space that just sucks everything in, this hungry void that devours stars and planets and light itself. And yeah, okay, there's some truth to that image, but it's also, well, it's not quite right. It's not right in ways that are actually far more interesting, far more strange than the simple picture we usually get. Because black holes aren't really holes at all, not in any sense that we normally use that word. They're not tunnels or openings or portals to somewhere else. They're objects, incredibly dense, incredibly massive objects. And what they do to the fabric of reality itself, what they tell us about the nature of space and time and matter, that's where things get really, really interesting. You see, when we talk about black holes, we're not just talking about some exotic astronomical phenomenon that exists way out there in the distant cosmos, completely separate from our everyday lives. We're talking about something that challenges our most fundamental assumptions about how the universe works. What is time? What is space? What happens to information, to matter, to light itself when it encounters something so extreme that the normal rules seem to break down? These aren't just academic questions, they're questions that go to the heart of what reality actually is. And black holes, these strange dark objects scattered throughout the universe, they're like laboratories where nature shows us what happens when you push physics to its absolute limits. So let me start with something that seems simple but actually isn't. What is a black hole? The standard answer you'll get is something like, it's a region of space-time where gravity is so strong that nothing, not even light, can escape. And that's true as far as it goes. But that definition, while accurate, it kind of misses the deeper strangeness of what's actually going on. Because to understand black holes, you first have to understand something pretty radical about gravity itself. Gravity isn't a force in the way we usually think about forces. It's not like magnetism or electricity, where one thing pushes or pulls on another thing across empty space. No, gravity is something much weirder than that. Gravity is the curvature of space-time itself. That's a phrase you've probably heard before, right? Space-time curvature. But what does it actually mean? Well, and this is where it starts to get interesting. We have to talk about Einstein. Albert Einstein, working in the early 20th century, he revolutionized our understanding of pretty much everything. Before Einstein, everyone thought about space and time as these separate absolute things. Space was this empty container where stuff happened, and time was this universal clock that ticked away the same for everyone everywhere. Newton's universe was like a stage where the drama of physics played out, but the stage itself never changed. It was fixed, immutable, eternal. But Einstein, he showed us that's not how it works at all. Space and time aren't separate things. They're woven together into this single thing we call space-time. It's a four-dimensional fabric, if you will, where the three dimensions of space and the one dimension of time are all mixed up together in ways that seem impossible until you really dig into the mathematics. And here's the really wild part. This fabric, this space-time, it's not rigid. It's flexible. It can bend and warp and curve. And what causes it to curve? Mass, energy, matter. When you put a massive object somewhere in space, it doesn't just sit there in some empty void. It actually warps the space-time around it, creates a kind of depression or curvature in the fabric of reality itself. The analogy everyone uses, and it's not perfect, but it helps, is to imagine space-time as a rubber sheet stretched out flat. Now put a bowling ball in the middle of that sheet. What happens? The sheet sags, right? It creates this depression, this curved region around the ball. And if you roll a marble near that depression, it doesn't travel in a straight line anymore. It curves toward the bowling ball, following the contours of the warped sheet. That's what we call gravity. It's not the bowling ball reaching out and pulling the marble. It's the marble following the curved path through space-time that the bowling ball has created. Now, that analogy breaks down in all sorts of ways, and we'll get to those, but it gives you the basic idea. Gravity is geometry. It's the shape of space-time. And when Einstein published his general theory of relativity in 1915, laying all this out in beautiful, complex mathematics, he gave us a completely new way of understanding the universe. But here's the thing. Even Einstein didn't immediately realize all the implications of his own theory. The equations of general relativity are notoriously difficult to solve. They're non-linear partial differential equations that describe how matter and energy curve space-time and how that curved space-time tells matter and energy how to move. It's this beautiful feedback loop, this dance between geometry and physics. But actually solving those equations for realistic situations, that's incredibly hard. Which brings us to a guy named Karl Schwarzschild. In 1916, just a few months after Einstein published General Relativity, Schwarzschild was serving as a German soldier in World War I, stationed on the Russian front. And while he was there, in the trenches, dealing with everything that entails, he was also doing physics. He was working on Einstein's equations, and he found something remarkable, an exact solution. He discovered that for a perfectly spherical, non-rotating mass, you could solve Einstein's equations exactly. And the solution showed something weird. It showed that there was a particular radius, a critical distance from the center of the mass, where something strange happened, where the curvature of space-time became so extreme that it created a point of no return. We call that radius the Schwarzschild radius, named after him. And the surface at that radius we call the event horizon. If you compress any amount of mass down into a sphere smaller than its Schwarzschild radius, you create a black hole. For Earth, just to give you a sense of scale, the Schwarzschild radius is about 9 millimeters, less than a centimeter. If you could somehow compress the entire Earth down to the size of a marble, you'd create a black hole. For the Sun, it's about 3 kilometers. Our Sun, which is about 1.4 million kilometers across, if you squeezed it down to a ball just 3 kilometers in radius, it would become a black hole. But here's what's important to understand. The Schwarzschild radius isn't determined by some property of the object itself, some physical material or structure. It's determined purely by mass. More mass means a larger Schwarzschild radius. A supermassive black hole, the kind you find at the center of galaxies, might have a Schwarzschild radius of millions of kilometers. But the key thing, the crucial thing, is this. Once you cross that boundary, once you pass through the event horizon, the geometry of space-time is so warped that all paths, every possible trajectory through space-time, they all lead inward, toward the center. There is literally no way out, not because something is holding you there with a force, but because the structure of space-time itself has been bent so severely that outward isn't even a direction you can move in anymore. Think about it like this. Imagine you're on the surface of the Earth, standing at the North Pole. If you start walking in any direction, you're moving south, right? There is no direction you can walk that takes you more north because you're already at the most northern point. Now imagine that same situation but with time instead of space. Inside the event horizon of a black hole, moving forward in time necessarily means moving toward the center of the black hole. Just as you can't move backward in time in normal space-time, you can't move away from the center once you're inside the horizon. The center of the black hole is literally in your future, unavoidably, inevitably. That's not a metaphor. That's what the geometry of space-time inside a black hole actually looks like. And this is where people often get confused about what black holes are and how they work. They think of the event horizon as some kind of physical surface, maybe something like a membrane or a boundary made of some exotic material. But it's not. It's not a thing you can touch or see or interact with directly. It's a surface in space-time, a mathematical boundary where the geometry changes in a fundamental way. If you were falling toward a black hole, you wouldn't see or feel anything special as you crossed the event horizon. Not if the black hole was large enough anyway. You'd just keep falling. The space around you would look normal. Well, mostly normal. There wouldn't be a sign that says, "You are now crossing the event horizon. There's no turning back." It would just happen. And only later would you realize that your fate was sealed, that you were now inevitably headed toward the center, toward the singularity. The singularity. That's the really troubling part. The place where our physics breaks down completely. At the very center of a black hole, according to Einstein's equations, all the mass that collapsed to form the black hole, all of it, it gets compressed down to a single point. A mathematical point with zero volume and infinite density. Now, when physicists get answers like infinite density from their equations, that's usually a sign that something's wrong. It means we're pushing our theories beyond their limits into regimes where we don't really know what's happening anymore. And that's almost certainly what's going on with the singularity. We don't actually think there's a point of infinite density at the center of black holes. We think that's where quantum mechanics, the physics of the very small, has to come into play. But we don't have a complete theory of quantum gravity yet, so we don't know what really happens there. The singularity is like a sign that says, "Here be dragons. We need new physics to understand this." But let me back up a bit because I'm getting ahead of myself. I want to talk about how black holes actually form in nature, because they're not just theoretical constructs, they're real objects out there in the universe. And we've actually observed them, detected them, studied them. The most common way a black hole forms is through the death of a massive star. You see, stars are these incredible balancing acts. They're fighting against their own gravity every moment of their lives. A star is basically a giant ball of gas, mostly hydrogen, and that gas wants to collapse inward under its own gravitational attraction. What keeps it from collapsing? Nuclear fusion. In the core of the star, hydrogen atoms are being fused together to form helium, and that process releases enormous amounts of energy. That energy creates pressure, an outward push that balances the inward pull of gravity. And as long as the star has fuel to fuse, as long as it can maintain that fusion reaction in its core, it stays stable. But eventually, inevitably, the star runs out of fuel. For smaller stars like our Sun, this happens relatively gently. The star expands into a red giant, sheds its outer layers, and leaves behind a dense core called a white dwarf. White dwarfs are held up not by fusion, but by something called electron degeneracy pressure, a quantum mechanical effect that keeps the electrons from being squeezed too close together. And that's fine for stars up to a certain mass. But for stars much more massive than the Sun, stars with maybe 10 or 20 or 50 times the Sun's mass, things go very differently. These massive stars, they burn through their fuel much faster. They're profligate, wasteful with their hydrogen. And as they age, they start fusing heavier and heavier elements. Hydrogen to helium, helium to carbon and oxygen, then on to neon, magnesium, silicon, and finally iron. And iron is where the chain stops. You can't get energy out of fusing iron. In fact, fusing iron costs energy. So when a massive star builds up an iron core in its center, that's it. The fusion stops. And suddenly, there's nothing holding the star up against its own gravity. What happens next happens fast, incredibly fast. The core collapses. In less than a second, a core the size of the Earth collapses down to a ball maybe 20 kilometers across. The gravitational potential energy released in this collapse is enormous, more energy than the star has emitted in its entire lifetime, and most of it comes out in the form of neutrinos. But some of it drives a shockwave outward through the star's outer layers, blowing them off in what we call a supernova. The explosion is so bright that for a few weeks, a single star can outshine an entire galaxy of hundreds of billions of stars. It's one of the most energetic events in the universe. And what's left behind in the center is the collapsed core. If that core is massive enough, if it has more than about 3 times the mass of the Sun, then not even neutron degeneracy pressure, the quantum force that keeps neutrons apart, can hold it up. There's nothing left to stop the collapse. The core just keeps collapsing, getting denser and denser, warping space-time more and more severely until it collapses past its Schwarzschild radius. And at that moment it becomes a black hole. An event horizon forms. The matter continues collapsing inward toward the singularity. But from the outside, from our perspective, all we can see is this dark, silent object, a region of space from which nothing can escape. Now you might be wondering, if nothing can escape from a black hole, not even light, how do we know they exist? How can we observe something that's literally invisible? And that's a great question, because it gets at the nature of how we do astronomy and astrophysics. We can't see black holes directly, that's true, but we can see their effects on things around them. A black hole doesn't just sit there doing nothing, it affects its environment in very noticeable ways. First, there's gravity. Black holes are massive, and that means they pull on things nearby. If a black hole is part of a binary system orbiting around another star, we can watch that star wobble back and forth, and from the characteristics of that wobble, we can infer that there's something massive there, something we can't see. That's how astronomers found some of the first strong black hole candidates back in the 1970s. They observed stars in binary systems that were orbiting around invisible companions that were too massive to be white dwarfs or neutron stars. The only thing they could be, given their mass and invisibility, was black holes. But there's another way black holes reveal themselves, and it's actually quite dramatic. When matter falls toward a black hole, it doesn't just drop straight in. Because of angular momentum, because of the rotation in the system, matter typically forms what we call an accretion disk. It's a disk of gas and dust and plasma spiraling inward toward the event horizon, and as that matter spirals inward, it heats up enormously. The friction and compression in the accretion disk can heat the material to millions of degrees, and when gas gets that hot, it radiates X-rays, intense, bright X-rays. So paradoxically, even though black holes themselves are dark, the region just outside a black hole, the accretion disk, can be one of the brightest objects in the universe. We detect black holes by observing the X-rays coming from matter just before it disappears past the event horizon. And in recent years, we've developed even more remarkable ways to detect black holes. In 2015, the LIGO Observatory made one of the most important discoveries in modern physics. They detected gravitational waves. These are ripples in space-time itself, predicted by Einstein a century earlier, but never directly observed until then. And what created these gravitational waves? 2 black holes, each about 30 times the mass of the Sun, spiraling together and merging. As they orbited each other faster and faster, getting closer and closer, they churned up the fabric of space-time, sending out waves that spread across the universe at the speed of light. By the time those waves reached Earth, over 1 billion years after the collision, they were incredibly faint. They stretched and squeezed space by an amount smaller than the width of a proton. But LIGO was sensitive enough to detect them. That detection, it opened up a whole new window on the universe. We'd spent centuries observing the cosmos with light, electromagnetic radiation in all its forms. But gravitational waves are something completely different. They let us observe events and objects that don't emit light at all. And since then, LIGO and other gravitational wave detectors have observed dozens of black hole mergers, and each one teaches us something new about these objects, about how they form, how they evolve, how common they are in the universe. And then, in 2019, we got something even more remarkable. The Event Horizon Telescope collaboration released the first actual image of a black hole. Not an artist's impression or a simulation, but an actual image constructed from radio telescope observations. They looked at the supermassive black hole at the center of a galaxy called M87, about 55 million light years away. This black hole has a mass of about 6.5 billion times the mass of the Sun. It's enormous, and what the image showed was this glowing ring of light surrounding a dark central region, a shadow. That shadow is the black hole itself, or rather, it's the region around the black hole where light can't escape. The glowing ring is the accretion disk, matter swirling around the black hole at incredible speeds, heated to billions of degrees, emitting radiation that we can detect here on Earth. Seeing that image, for me at least, it was profound, because black holes had been theoretical for so long, right? They were predictions of mathematics, solutions to equations, things we inferred from indirect observations. But that image made them real in a visceral way. There it was, a shadow in space-time, a region where reality itself is so warped that light cannot escape. It's one thing to understand black holes intellectually, to work through the equations and see how they emerge from the theory. It's another thing entirely to see one, even if what you're seeing is the absence of light rather than light itself. But let me shift gears a bit, because there's an aspect of black holes that's even stranger than anything I've talked about so far. And that's what happens to time near a black hole. You see, one of the key insights of relativity is that time is not absolute. Time doesn't flow at the same rate everywhere in the universe. It depends on how fast you're moving and how strong the gravitational field is where you are. Near a massive object, time runs slower. This is called gravitational time dilation, and it's been tested and confirmed many times. The GPS satellites orbiting Earth, for example, they have to account for time dilation. Time runs slightly faster in orbit than it does on the surface because the gravitational field is weaker up there. If we didn't correct for this, GPS wouldn't work. Your phone couldn't figure out where you are. But near a black hole, time dilation becomes extreme. Let's say you're watching someone fall toward a black hole from a safe distance away. What would you see? Well, as they get closer and closer to the event horizon, something strange starts to happen. They appear to slow down. Their movements become more and more sluggish. Light from them becomes increasingly red-shifted, stretched out to longer and longer wavelengths, dimmer and dimmer. And as they approach the event horizon, they appear to freeze. They never quite seem to cross it, not from your perspective. They just get dimmer and redder and appear to slow asymptotically toward a standstill. It would take an infinite amount of time, as measured by your clock, for them to reach the horizon. But from the perspective of the person falling in, things are completely different. They don't experience any slowing down at all. From their point of view, time passes normally. They reach the event horizon in a finite amount of time, cross it, and continue falling toward the center. The time dilation is not something they feel or experience directly. It's only relative to observers far away. This is one of the deeply weird things about relativity. Time is not universal. Different observers in different reference frames, experiencing different gravitational fields, they measure time differently. And near a black hole, those differences become dramatic. There's a thought experiment that really brings this home, and it's kind of disturbing if you think about it too carefully. Imagine you and a friend are near a black hole. Your friend decides to fall in while you stay safely away. As they fall, they're sending radio signals back to you constantly, let's say 1 signal per second by their watch. What do you observe? At first, the signals come regularly, but as your friend gets closer to the event horizon, the signals start arriving farther and farther apart. One per second becomes one every 2 seconds, then every 10 seconds, then every minute, every hour. The signals are also getting redshifted, the frequency shifting down, until eventually they're shifting into infrared, then radio waves, then wavelengths so long that they're essentially undetectable. The last signal you receive from your friend, for all practical purposes, arrives right before they cross the horizon. After that, silence. Not because they stopped sending signals, but because those signals are infinitely redshifted, stretched out so much that they never actually reach you. Meanwhile, from your friend's perspective, they cross the horizon maybe 10 seconds after they started falling. They're still sending signals, but those signals, once emitted from inside the horizon, they can't escape. They're trapped just like everything else. To you, your friend appears frozen at the event horizon forever, dimly glowing, gradually fading away. To your friend, they crossed into the black hole and are now falling toward the singularity, with only minutes or maybe hours left before they reach it, depending on the size of the black hole. Both perspectives are valid, both are true. That's what relativity means. Reality itself is not absolute. It depends on your frame of reference, on where you are and how you're moving. And this raises all sorts of fascinating and troubling questions. If nothing can ever be seen to cross the event horizon from the outside, in what sense does anything ever fall in? Well, in a very real sense, from the perspective of the universe outside the black hole, nothing does cross the horizon, not in finite time. But from the perspective of an infalling observer, they most definitely do cross, and quite quickly. Both views are correct because they're measuring time differently. This isn't a contradiction, it's just how space-time works near an extreme gravitational field. Now, what would actually happen to you if you fell into a black hole? This is a question that comes up a lot, and the answer depends on the size of the black hole. For a small black hole, one with just a few times the mass of the sun, the experience would be brief and unpleasant, very unpleasant. You'd encounter something called tidal forces. Tidal forces arise because gravity gets stronger as you get closer to a massive object. Your feet, which are closer to the black hole, would feel a much stronger gravitational pull than your head. The difference in the gravitational field over the length of your body would stretch you. We call this spaghettification, which is maybe a little too whimsical a term for something that would tear you apart at the molecular level. Long before you reach the event horizon of a small black hole, the tidal forces would rip you to shreds. But for a supermassive black hole, the kind at the center of a galaxy, things are different. Larger black holes have gentler tidal forces at their event horizons. The event horizon of a supermassive black hole might be millions of kilometers in radius. And at that distance, the tidal forces could actually be quite mild. You could cross the event horizon and not feel anything unusual. Space around you would seem flat, normal. You could still see stars, though they'd be distorted, bunched up toward certain directions because of the way the black hole bends light. You might not even realize you'd crossed the point of no return until you thought about it carefully. But then, as you continued falling inward, things would get stranger. The tidal forces would build. Eventually, they'd become overwhelming, and you'd be ripped apart just like with a smaller black hole, just later in the process. And you'd be falling toward the singularity, toward that point where space-time curvature becomes infinite, where our physics breaks down. What actually happens at the singularity, we don't know. Honestly, we don't. It's one of the great mysteries. Our theories stop working there. General relativity predicts its own demise, in a sense. It tells us that there's a place where its predictions become meaningless, where we need a new theory, a quantum theory of gravity, to tell us what really happens. Some physicists think that the singularity might not be a point at all. Maybe quantum effects prevent the collapse from going all the way to zero volume. Maybe there's some minimum size, some quantum bounce, or something else entirely that we haven't imagined yet. But without a working theory of quantum gravity, we're just speculating. Then the singularity remains a place where our understanding ends, a boundary to human knowledge, at least for now. But here's something that makes this even more interesting, more mysterious. In 1974, Stephen Hawking discovered something completely unexpected. He showed that black holes aren't entirely black. They emit radiation. Now, This seems impossible, right? Nothing can escape from inside the event horizon. That's the definition of a black hole. So how can they radiate? Well, the radiation doesn't come from inside the horizon. It comes from right outside it, from the quantum vacuum near the event horizon. And to understand this, we need to talk a little about quantum mechanics. In quantum mechanics, the vacuum isn't really empty. It's seething with activity, with particle-antiparticle pairs constantly popping into existence and then annihilating each other almost immediately. These are called virtual particles, and they exist for such a short time that they don't violate conservation of energy because of Heisenberg's uncertainty principle. This happens everywhere, all the time, but normally we don't notice it. These virtual particles appear and disappear without any lasting effect. But near the event horizon of a black hole, something interesting can happen. A particle-antiparticle pair can appear right at the horizon, and before they can annihilate, one of them can fall into the black hole while the other escapes. To a distant observer, it looks like the black hole is emitting particles, and it is, in a sense. But those particles are coming from the vacuum, energized by the gravitational field of the black hole. And here's the crucial bit. When a particle escapes as Hawking radiation, the black hole loses a tiny bit of mass and energy. The black hole is evaporating very slowly, gradually giving up its mass to the universe. For a large black hole, this process is incredibly slow. A black hole with the mass of the Sun would take something like 10 to the 67th power years to evaporate completely, far longer than the current age of the universe. But the smaller the black hole, the faster it evaporates, and as it shrinks, it gets hotter and radiates faster. A tiny black hole, one with the mass of a mountain but the size of an atom, would be incredibly hot and would evaporate explosively in a burst of radiation. We haven't observed any black holes evaporating because all the ones we know about are too large. But the theoretical prediction is there, and it has profound implications. For one thing, it means black holes have a temperature. They're thermodynamic objects. They have entropy, a measure of disorder or information content. And the entropy of a black hole, Hawking showed, is proportional to the area of its event horizon, not its volume. That's weird. For normal objects, entropy is proportional to volume, to the number of particles or the amount of stuff. But for black holes, it's the surface area that matters. This led to ideas about the holographic principle, the notion that all the information in a three-dimensional region of space can be encoded on a two-dimensional surface surrounding it. Black holes might be telling us something fundamental about the nature of information and reality. And this brings us to one of the deepest puzzles in theoretical physics, the black hole information paradox. Here's the problem. According to quantum mechanics, information is never truly destroyed. If you know the quantum state of a system perfectly at one time, you can in principle calculate its state at any other time, forward or backward. The laws of quantum mechanics are reversible. Information is conserved. But what happens if you throw something into a black hole? That object carries information, quantum information about its state, and once it's inside the horizon, that information seems to be lost to the outside universe. You can't get it back. Now, if black holes were truly eternal, that might be okay. The information would still exist, just hidden behind the horizon, inaccessible, but not destroyed. But Hawking radiation changes things. If black holes evaporate, if they eventually disappear completely, what happens to the information? The Hawking radiation is thermal, random. It doesn't carry any information about what fell into the black hole, so it seems like the information is destroyed, vanished from the universe. But that violates the fundamental principles of quantum mechanics. That's the paradox. Physicists have been wrestling with this for decades now. Some think the information is somehow encoded in the Hawking radiation in subtle ways we don't yet understand. Others propose that information is stored at the event horizon, perhaps in some structure we haven't discovered. There are ideas involving things called firewalls, dramatic modifications to our understanding of what the event horizon is like. Some researchers even suggest that black holes might not completely evaporate, that they might leave behind stable remnants that preserve the information. And some think the paradox is telling us that our understanding of space-time itself is incomplete, that at the deepest level, space-time might be an emergent phenomenon arising from something more fundamental, and black holes are showing us where our current picture breaks down. The truth is, we don't have a definitive answer yet. The information paradox remains an open question, one of the big clues that might guide us toward a theory of quantum gravity, toward a deeper understanding of how the universe works at the most fundamental level. And that's exciting, isn't it? That there are still mysteries like this, deep conceptual problems that challenge our best theories and push us to think harder, to develop new ideas, to imagine possibilities we haven't considered yet. Let me talk a bit about the supermassive black holes, because they're fascinating in their own right, and they play a crucial role in the evolution of galaxies. At the center of most large galaxies, including our own Milky Way, there's a supermassive black hole. These aren't just big black holes, they're enormous, with masses ranging from millions to billions of times the mass of the Sun. The one at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns, and we've watched stars orbit around it, tracing out elliptical paths that reveal the presence of this massive, dark object at the galactic center. How do supermassive black holes form? That's actually still somewhat mysterious. They're too massive to have formed from a single star, so they must have grown over time. Maybe they started as smaller black holes, perhaps from the very first generation of stars in the early universe, and then grew by accreting matter and merging with other black holes. Or maybe they formed more directly from the collapse of massive gas clouds in the early universe. We're not entirely sure. But what we do know is that they play a critical role in galaxy evolution. The energy released by matter falling into a supermassive black hole, the energy from the accretion disk and from jets of material that can be launched from near the black hole, this energy can affect the entire galaxy. It can heat up gas, preventing it from cooling and collapsing to form new stars. It can drive galactic winds, blowing gas out of the galaxy entirely. This feedback from supermassive black holes seems to regulate star formation in galaxies, to determine how big galaxies can grow, to shape the properties of galaxies across the universe. There's this intricate dance between the growth of the supermassive black hole and the growth of the galaxy around it. They influence each other, and understanding that relationship is crucial to understanding how galaxies form and evolve over cosmic time. And here's something that blows my mind every time I think about it. The supermassive black hole at the center of the Milky Way, Sagittarius A star, is about 26,000 light years away from us. We're orbiting around it, along with all the other stars in the galaxy. It takes the Sun about 230 million years to complete one orbit around the galactic center. And that black hole, as massive and influential as it is, it only affects the very central region of the galaxy directly. Out here where we are, its gravitational influence is no stronger than it would be if that same mass were distributed in stars. The black hole doesn't exert some special pull just because it's a black hole. Gravity depends on mass and distance, not on what form the mass takes. If the Sun suddenly became a black hole of the same mass, which can't actually happen because the Sun isn't massive enough, but bear with me, Earth's orbit wouldn't change at all. We'd keep orbiting at the same distance, the same speed. We'd just be very cold and dark. So black holes aren't cosmic vacuum cleaners, not really. They don't reach out across vast distances and suck things in. You could orbit a black hole just like you orbit a star, as long as you stayed outside the event horizon and away from the accretion disk. It's only if you get very close, if you cross that event horizon, that escape becomes impossible. And for a supermassive black hole, the event horizon might be far enough away from the center that you could live your entire life in orbit around it, never feeling anything unusual, except for the fact that there's this dark region in the sky, this shadow where no light comes from. I want to talk about something that's been on my mind, something about what black holes represent philosophically, existentially, because they're not just astrophysical objects, right? They're also concepts that challenge how we think about reality, about time, about the nature of existence itself. A black hole is a place where our understanding reaches its limits. It's a physical manifestation of the boundaries of human knowledge. And there's something both humbling and exhilarating about that. We've built these incredible theories, general relativity and quantum mechanics, and they've been astonishingly successful. They've predicted phenomena that seem impossible, that defy common sense. And yet when we go out and look, we find that nature behaves exactly as the theories say it should. The precision of these theories is remarkable, but black holes, particularly their interiors and their singularities, they show us where our theories break down. They show us that we don't have the complete picture yet. And that's okay. That's how science works. Theories are always provisional, always subject to revision when we encounter phenomena they can't explain. But it's more than that. Black holes raise questions about the nature of time in a way that's deeply unsettling if you really think about it. Inside the event horizon, the roles of time and space get mixed up in a strange way. The singularity isn't just a place in space that you might reach. It's a moment in your future, an event that you're inevitably approaching if you're inside the horizon. You can no more avoid reaching the singularity than you can avoid tomorrow. The future becomes a direction in space in some sense. That's profoundly weird. Our normal intuitions about space and time, they just don't apply. The structure of reality inside a black hole is fundamentally different from anything we experience in our everyday lives. And then there's the question of determinism. In classical physics, if you know the state of a system now, you can predict its future and retrodict its past with perfect accuracy, at least in principle. Quantum mechanics complicates this with inherent randomness and uncertainty, but there's still a sense in which information is preserved, in which the quantum state evolves according to deterministic equations. But black holes seem to violate this. If information can be destroyed in a black hole, then the universe is not deterministic in even the quantum sense. The future is not determined by the present. And that's troubling, not just philosophically, but for the consistency of our physical theories. Some physicists have suggested that maybe the event horizon isn't quite what we think it is. Maybe there are subtle quantum effects that modify the horizon, that prevent information from being truly lost. Maybe the horizon is more like a membrane that processes and encodes information rather than a simple boundary. These ideas lead to concepts like the holographic principle I mentioned earlier, the idea that the information content of a volume of space is actually encoded on its boundary. If that's true, then a black hole's event horizon contains all the information about everything that's fallen in, encoded in some way that we don't yet fully understand. And when the black hole evaporates via Hawking radiation, that information is released back into the universe, not lost. The holographic principle suggests something even more radical, that the three-dimensional world we experience might itself be a kind of hologram, a projection of information encoded on a distant two-dimensional surface. Black holes might be giving us hints about the true nature of space-time and reality. There's also been speculation, and this is pretty far out there, but it's worth mentioning about what happens inside a black hole. Some models suggest that the conditions inside a black hole, the extreme warping of space-time, might be similar to the conditions at the Big Bang. Could the interior of a black hole be a region where a new universe is born? Could our own universe be inside a black hole in some larger space? These are ideas that are hard to test, maybe impossible to test, but they're fascinating to think about. They point to a universe, or perhaps a multiverse, that's far stranger and more complex than we normally imagine. And you know what strikes me? It's that black holes are real. They're not just mathematical curiosities or thought experiments. They're out there, thousands of them in our galaxy alone, millions or billions of them across the observable universe. Every large galaxy has a supermassive black hole at its center. Stellar mass black holes are scattered throughout the galaxy, remnants of massive stars that died long ago, and we've detected them, we've measured their masses, observed their effects, seen them merge, even imaged the shadow of one. The universe is full of these regions where space-time is torn, where reality is warped beyond recognition, where time and space exchange roles, where our physics reaches its limits, and they're just there, existing, doing their thing, part of the natural fabric of the cosmos. It makes you wonder, doesn't it? What else is out there that we haven't discovered yet? What other phenomena are waiting at the edges of our understanding, ready to overturn our assumptions and show us that the universe is stranger than we thought? Black holes were once considered almost absurd, too bizarre to be real. Einstein himself was skeptical that they could actually form in nature, but they do. Nature is under no obligation to conform to our intuitions or preferences. It just is what it is, and our job is to figure it out, to build theories and models and test them against observation, to gradually expand the sphere of human understanding. Let me think about the future for a moment, about where research on black holes is headed and what we might learn in the coming decades. We're entering a really exciting era for black hole astronomy. The detection of gravitational waves has opened up a completely new way to study these objects. With each black hole merger we observe, we learn more about their population, their masses, their spins, how they form, how common they are. We're starting to build up a statistical picture of black holes across cosmic time. And the Event Horizon Telescope, the project that imaged the black hole in M87, they're continuing their work. They've now imaged Sagittarius A star, the black hole at the center of our own galaxy. That was technically even more challenging than M87 because Sagittarius A star is much smaller and the material around it varies much more quickly. But they did it. And future observations, with more telescopes and better techniques, will give us even sharper images, will let us study the dynamics of the accretion disk, will test general relativity in the strong field regime around black holes with unprecedented precision. There are also proposals for space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna. This would be sensitive to lower frequency gravitational waves than LIGO can detect, waves from supermassive black hole mergers, events that happen when galaxies collide and their central black holes spiral together. Observing these events would teach us about galaxy evolution, about the growth of supermassive black holes, about the dynamics of space-time on truly enormous scales. And on the theoretical side, there's intense work on quantum gravity, on trying to understand what happens at the singularity, on resolving the information paradox. String theory, loop quantum gravity, other approaches are all trying to build a framework that can describe the quantum properties of space-time itself. Black holes are one of the key testing grounds for these ideas. They're the place where quantum effects and gravitational effects are both strong, where any successful theory of quantum gravity has to make predictions that we can hopefully test, at least indirectly. Some researchers are exploring the possibility that the information paradox might require us to rethink our understanding of locality, of how information is stored and transmitted in space-time. There are ideas about quantum entanglement playing a crucial role in the structure of space-time itself, with connections between entanglement and the geometry of space. It's deep, heady stuff, and honestly, a lot of it is still speculative. But it's driven by the mysteries that black holes present, by the need to reconcile quantum mechanics and general relativity to build a consistent picture of how the universe works at all scales. And there's something profound about the fact that we can think about these things at all. We're these tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, and yet we can figure out what happens at the event horizon of a black hole. We can predict that gravitational waves exist and then build instruments sensitive enough to detect them. We can image the shadow of a black hole 55 million light years away. We can think about the quantum structure of space-time, about information and entropy and the nature of reality itself. That capacity, that ability to understand the universe, it's one of the most remarkable things about being human. Of course, there's so much we still don't know. How exactly do supermassive black holes form? What's the distribution of intermediate mass black holes, those between stellar mass and supermassive? Do they exist in significant numbers? What really happens at the singularity? Is information preserved or destroyed? What is the correct theory of quantum gravity? These are all open questions, and answering them will require more observations, more experiments, more theoretical work. It will take time, effort, creativity. But that's the nature of science. It's an ongoing process, a journey rather than a destination. Let me come back to something more immediate, more tangible. What would it actually look like to be near a black hole? I mentioned earlier that if you fell into one, you might not notice crossing the event horizon, but the view, the appearance of the sky around you would be strange and beautiful. Black holes bend light, right? They warp space-time, and light travels along curved paths near them. So if you were in orbit around a black hole, looking out at the stars, you'd see distortions. Stars that are actually behind the black hole could appear above or below it because their light has been bent around it. You'd see multiple images of the same star, perhaps light taking different paths around the black hole to reach your eyes. The black hole itself would appear as a dark circle, a shadow, but it would be larger than you might expect, about 2.6 times the radius of the event horizon, because of the way light is captured and bent in the region around the horizon. And if the black hole had an accretion disk, you'd see that glowing brilliantly, a disk of superheated matter swirling around the darkness. But even the disk would look strange. Because of the extreme velocities and gravitational effects, you'd see relativistic beaming, where material moving toward you appears brighter and material moving away appears dimmer. You'd see Doppler shifts, the light from the approaching side of the disk shifted to blue and the receding side shifted to red. And if you were close enough, you might see light from the far side of the disk appearing above and below the black hole, bent around it by gravity, creating this complex layered image that doesn't look like anything we see in our everyday experience. There's a certain beauty to it, a geometric beauty. Black holes are some of the simplest objects in the universe, in a sense. They're described by just a few parameters: mass, spin, and electric charge, though realistic black holes probably don't have much charge. That's it. No other details, no complexity. We call this the no-hair theorem, the idea that black holes have no distinguishing features, no hair. All the complexity of whatever fell in to make the black hole is gone, leaving behind this simple, pure geometric object. And yet, the behavior of matter and light near a black hole can be incredibly complex, incredibly rich, full of structure and dynamics and fascinating phenomena. I think about the scientists who first worked all this out, who looked at Einstein's equations and realized what they were saying, who had the courage to take the math seriously, even when it led to conclusions that seemed absurd. Karl Schwarzschild, working in the trenches of World War I, solving Einstein's equations and finding a solution that implied the existence of these bizarre objects. Roy Kerr, who in 1963 found the solution for a rotating black hole, a more realistic and even stranger case where space-time is not only curved, but twisted, dragged around by the spinning black hole. John Wheeler, who coined the term black hole in 1967, and did so much to make them respectable subjects of scientific inquiry. Roger Penrose, who proved theorems about singularities and the inevitability of collapse under certain conditions, who showed that singularities weren't just artifacts of special symmetries, but generic features of gravitational collapse. Stephen Hawking, who brought quantum mechanics into the picture and showed that black holes are thermodynamic objects, that they radiate, that they connect quantum theory and gravity in deep and mysterious ways. These people, and many others, they built up our understanding piece by piece. And it's still ongoing. There are hundreds of researchers around the world working on black holes right now from different angles with different tools and methods. Some are observing them with telescopes, studying their effects on stars and gas. Some are detecting gravitational waves, listening to the space-time ripples from black hole mergers. Some are doing simulations on supercomputers, modeling the complex physics of accretion disks and jets. Some are working on pure theory, trying to understand the quantum mechanics of horizons, the nature of singularities, the information paradox. It's a collective effort, a human endeavor to understand something fundamental about the universe. And what we've found is that black holes are woven into the fabric of the cosmos in ways we didn't expect. They're not just exotic curiosities on the fringes of astrophysics. They're central players in the story of the universe. They regulate galaxy formation. They produce some of the most energetic phenomena we observe. They're laboratories for testing our most fundamental theories. They're signposts pointing toward new physics, toward a deeper understanding of reality. I wonder sometimes what it would be like to actually explore a black hole, to send a probe into one, to see what happens. Of course, we couldn't get the information back out. Anything that crosses the event horizon can't send signals back. But just knowing what happens, even if only the probe itself could know, there's something appealing about that. Though I suppose it's a moot point because any probe we sent would be destroyed by tidal forces well before it got anywhere interesting. And even if we could build a probe that could survive, the time dilation effects mean that it would take effectively forever from our perspective for it to cross the horizon. We'd see it slow down, freeze, fade away, but never quite cross. The probe itself, if it had a consciousness, would experience crossing and would continue falling toward the singularity, but we'd never know what it found. It's a fundamental limitation, a horizon in the most literal sense, beyond which we cannot see. That's one of the humbling things about black holes. There are limits to knowledge, places we can't go, questions we can't answer through direct observation, but we can still learn about them indirectly through theory and through clever observations of their effects. We can still build models, make predictions, test those predictions. Science is good at that, at finding ways around obstacles, at extracting information from systems in creative ways. And who knows, maybe someday we'll have a complete theory of quantum gravity and we'll be able to calculate from first principles what happens at the singularity, what the structure of space-time is like in those extreme conditions. We might never be able to verify it directly, but if the theory makes predictions about other things that we can test, and if those predictions keep being confirmed, then we'll have good reason to trust what it says about black holes. There's also the question, and this is more philosophical than scientific, of whether black holes might be connected to other regions of space-time, to other universes perhaps. In the mathematics of general relativity, certain solutions, particularly the Kerr solution for rotating black holes, have structures called wormholes, bridges connecting different regions of space-time. In principle, you might be able to enter a black hole and exit from a white hole somewhere else rather than hitting a singularity. But these solutions are probably not physically realistic. They require exotic conditions, negative energy densities, things that might not actually exist in nature. And even if they did, the wormholes would be unstable, collapsing before anything could traverse them. But it's fun to think about, isn't it? The idea that black holes might be doors to other places, other times, other universes. It's the stuff of science fiction, and most physicists think it's just that, fiction. But the math allows for it, at least in certain idealized cases, and that's intriguing. It reminds us that space-time is more flexible, more strange than our everyday experience suggests. The fact that we can even ask questions like, could a black hole be a gateway to another universe? And explore them with equations and logic, that's remarkable. Now let me think about the concept of black hole entropy more carefully, because it really is one of the most profound discoveries in theoretical physics. Jacob Bekenstein in the early 1970s suggested that black holes must have entropy, that they're thermodynamic objects. His reasoning was based on the second law of thermodynamics, which says that entropy, the measure of disorder in a system, never decreases. If you drop something with entropy into a black hole, it disappears. If black holes didn't have entropy, the total entropy of the universe would decrease, violating the second law. So black holes must have entropy. And Hawking, working on the quantum mechanics of black holes, found that this entropy is proportional to the area of the event horizon. Specifically, the entropy is the area measured in Planck units, divided by 4. The Planck length is incredibly small, about 10 to the negative 35th meters, so the area of a black hole's event horizon, measured in Planck areas, is a huge number, and that's the entropy. For a black hole with the mass of the Sun, the entropy is something like 10 to the 77th power, an incomprehensibly large number. What does this mean? Entropy is usually thought of as a measure of the number of possible microscopic configurations that correspond to a given macroscopic state. For a gas, for example, there are many, many ways to arrange the molecules that all give the same temperature and pressure. That's the entropy. So if a black hole has entropy, it should have microscopic states, different possible configurations that all look the same from the outside. But what are those states? A black hole is just a region of curved space-time. What are the degrees of freedom, the things that can be in different configurations? We don't fully know. This is one of the mysteries. String theory suggests that the microscopic states are related to the quantum properties of strings and branes, exotic objects in higher dimensional spaces. Loop quantum gravity suggests they're related to the quantum geometry of space-time itself, to the discrete structure of space at the Planck scale. But these are just ideas, not fully developed theories that we can test. The fact that black holes have entropy, though, is a strong hint that there's more to space-time than what general relativity describes, that at some level space-time has a microstructure, a granularity, a set of degrees of freedom that give rise to this entropy. And the holographic principle, the idea that the information in a volume of space is encoded on its boundary, comes from thinking about black hole entropy. If entropy measures information, and if black hole entropy is proportional to area rather than volume, then maybe information is fundamentally two-dimensional, encoded on surfaces rather than in volumes. And maybe our three-dimensional experience of space is emergent, a consequence of this two-dimensional information structure. It's a radical idea, and it's not fully understood, but it comes directly from thinking about black holes. You see how black holes keep pushing us toward deeper questions. They don't just sit there being interesting astrophysical objects. They force us to confront the foundations of our theories, to ask questions about the nature of time, space, information, entropy, quantum mechanics, gravity. They're like keys that unlock doors to rooms we didn't even know were there. And every time we think we understand them, they reveal another layer of mystery, another puzzle to solve. I mentioned earlier that black holes aren't cosmic vacuum cleaners, that they don't reach out and pull things in from afar. But there is a sense in which they're the ultimate fate of certain objects in the universe. If you have a sufficiently massive star, it will collapse into a black hole when it dies. And once a black hole forms, it can only grow. It can accrete matter from its surroundings. It can merge with other black holes, but it can't shrink, at least not significantly, not on timescales that matter for astrophysics. Hawking radiation does cause black holes to evaporate, but for any astrophysical black hole, the timescale is so long that it's irrelevant. A solar mass black hole would take 10 to the 67th power years to evaporate. The universe is currently only about 1.4 times 10 to the 10th power years old. By the time Hawking radiation becomes significant, the universe will be a cold, dark, nearly empty place, with all the stars long since burned out, all the matter dispersed or locked up in black holes and stellar remnants. In fact, if you extrapolate far enough into the future, if you imagine the universe trillions upon trillions of years from now, black holes become the dominant objects. Stars will have died, galaxies will have dispersed, and what's left will be black holes, slowly evaporating, and eventually even they will be gone, leaving behind a universe that's essentially empty, just a thin soup of particles and radiation at an incredibly low temperature, approaching absolute zero. This is sometimes called the heat death of the universe, the final state of maximum entropy, where nothing interesting can happen anymore, because there are no gradients, no differences in temperature or density, nothing to drive change. But even that's not certain. Our understanding of the very long-term future of the universe depends on things we don't fully know, like the properties of dark energy, the mysterious stuff that's causing the expansion of the universe to accelerate. If dark energy remains constant, the universe will continue expanding forever, cooling and diluting, heading toward that heat death. But if dark energy changes over time, other scenarios are possible. The universe might recollapse in a big crunch, or the expansion might accelerate so much that even atoms are torn apart in a big rip. We don't know. But in most scenarios, black holes play a significant role in the far future, growing, merging, eventually evaporating, and possibly being among the last complex structures to exist before the universe reaches its final quiet state. There's something melancholy about that, I think, but also something profound. Black holes are, in some sense, the end point, the place where matter goes when gravity wins its final victory over all other forces. But they're also temporary, even if only on timescales so long they're hard to fathom. Everything in the universe, even black holes, even these objects that seem eternal and unchanging, they have a lifespan. They come into existence, they evolve, and eventually they evaporate away into radiation and particles, returning their mass energy to the cosmos. In the very longest view, nothing is permanent. Not stars, not planets, not galaxies, not even black holes. But right now, in our current epoch, black holes are vibrant, active objects. They're accreting matter, launching jets, merging with each other, shaping galaxies, teaching us about the universe. And we're in this golden age of black hole astronomy where we can study them in ways that would have seemed impossible just a few decades ago. We can detect their gravitational waves, we can image their shadows, we can watch stars orbit around them, we can measure their spins and masses with increasing precision. Each new observation refines our understanding, tests our theories, sometimes surprises us with something we didn't expect. And I think that's what makes science so compelling, so rewarding. It's not just about accumulating facts. It's about building understanding, about seeing connections, about recognizing patterns and structures in nature. Black holes connect so many different areas of physics. They involve gravity and quantum mechanics and thermodynamics and information theory and astrophysics and cosmology. To understand them fully, we have to understand all these pieces and how they fit together. And that's hard. That's why we haven't solved all the mysteries yet. But it's also why it's so interesting, why so many smart people dedicate their lives to working on these problems. There's a sense in which black holes are the most extreme natural laboratories in the universe. They let us test our theories under conditions we could never create artificially. The gravitational fields near a black hole are trillions of times stronger than anything we can produce on Earth. The energies in black hole accretion disks and jets rival those of the Big Bang itself. The quantum effects at the event horizon involve the deepest aspects of how quantum mechanics and gravity interact. By studying black holes, we're probing the limits of physics, seeing what nature does when all the dials are turned up to maximum. And sometimes nature surprises us. The first detection of gravitational waves from merging black holes, that event involved two black holes, each about 30 times the mass of the Sun. Before that detection, we weren't sure black holes that massive existed in nature. We thought maybe they'd be rare. But LIGO has detected dozens of them now. They're common. And that tells us something about stellar evolution, about how massive stars live and die, about the populations of black holes in the universe. It's data we didn't have before, and it's changed our understanding. Or consider the black hole in M87, the one that was imaged by the Event Horizon Telescope. That image confirmed predictions made decades earlier about what a black hole should look like, about the size of its shadow, about the structure of light around it. Seeing the theory confirmed so precisely, seeing that yes, general relativity really does describe what happens near a black hole's event horizon, that's incredibly satisfying. But there are also small discrepancies, little details in the observations that don't quite match the simplest models, and those discrepancies are interesting. They might be telling us about the dynamics of the accretion disk, or about the magnetic fields near the black hole, or possibly even about deviations from general relativity. We're still analyzing the data, still figuring it out. That's the process. Observe, theorize, predict, test, refine, round and round, getting closer and closer to the truth, never quite reaching complete certainty, but always improving our understanding. Black holes are part of that process. They're one of the many phenomena we're trying to understand, and they're one of the most challenging, which makes them one of the most interesting. I want to return to the human aspect of all this, the existential dimension, because black holes aren't just objects to study. They're also metaphors, symbols, things that resonate with us on a deeper level. The idea of a point of no return, a boundary you can cross but never return from, that resonates. It's a powerful image. And the fact that it's not just a metaphor, but a real physical thing, a place in the universe where this actually happens, that gives it weight. We live our lives moving forward in time, unable to go back, unable to undo the past. Every moment we're crossing our own personal event horizons, moving into futures that become presents and then pasts irretrievably. A black hole, in a sense, is a place where that one-way nature of time is made manifest in space as well. Once you're inside, all your possible futures lead to the singularity. You can't change that. You can't escape. It's a kind of ultimate determinism, a place where your fate is literally written into the geometry of space-time. And yet from a distance, from outside the event horizon, black holes are also places of incredible dynamism and energy. The accretion disks around black holes are some of the brightest objects in the universe. Matter spiraling into a black hole can release energy more efficiently than nuclear fusion. Black holes power quasars, the incredibly luminous objects we see in the distant early universe. They launch jets of particles and radiation that can extend for thousands of light years, affecting entire galaxies. So there's this duality. From the inside, a black hole is a place of inevitable doom, a geometric trap from which there's no escape. From the outside, it's a source of power, a cosmic engine driving some of the most spectacular phenomena in the universe. Maybe that's part of why black holes capture our imagination. They're paradoxical, they're simple yet complex. They're dark yet can be surrounded by brilliant light. They're solutions to elegant mathematical equations, yet they're connected to deep mysteries we haven't solved. They're out there in the physical universe, but they're also in here, in our minds. as we think about them, wonder about them, try to understand them. And in the end, maybe that's what the secret life of black holes is really about. It's not just about the physics, though. The physics is fascinating. It's about what black holes represent, what they teach us, how they challenge us. They're reminders that the universe is under no obligation to make sense to us, to conform to our intuitions. They're invitations to think more deeply, to question our assumptions, to imagine possibilities we hadn't considered. They're examples of how mathematical reasoning can reveal truths about the physical world that we'd never guess just from everyday experience. And they're beautiful in their way. Not in any visual sense necessarily, though images of accretion disks and gravitational lensing can be stunning, but beautiful in the sense that simple principles, applied rigorously, lead to profound and surprising conclusions. Beautiful in the way that a proof or a symphony or a poem can be beautiful, where everything fits together, where complexity emerges from simplicity, where understanding brings a sense of satisfaction and wonder. I started by saying, I've been thinking a lot about black holes, and I guess what I've come to is this. Black holes are one of the universe's ways of showing us who we are and where we fit. We're small, yes, we're fragile. We're bound to this tiny planet, unable to visit even the nearest stars, let alone a black hole. But we can think about black holes. We can understand them, at least partially. We can build instruments to detect them, theories to explain them, equations to describe them. We can look out into the cosmos and recognize what we're seeing, can trace the consequences of physical law across billions of light years and billions of years of time. That's not nothing. That's remarkable, actually, that we, made of star stuff, as Carl Sagan said, the products of billions of years of cosmic evolution, can contemplate the nature of space-time and gravity and quantum mechanics, can ask questions about what happens at the event horizon, at the singularity, in the final moments of evaporation, can wonder about information and entropy and the holographic principle, can send signals to each other across a planet, sharing ideas, building on each other's work, collectively constructing a picture of reality that's far more detailed and accurate than any individual could create alone. Black holes are out there, doing what they do, indifferent to our existence. But we're here, noticing them, studying them, learning from them. And that's the secret life of black holes, maybe. Not that they have secrets in the sense of hidden truths about themselves, though they do, but that they have a life in our minds, in our science, in our culture. They're part of the human story now, part of our understanding of the cosmos, part of what it means to be a species that asks questions and seeks answers. And there are more answers to find, more observations to make, more theories to develop, more mysteries to unravel. The information paradox remains unsolved. We don't have a theory of quantum gravity. We don't know what happens at the singularity. We don't fully understand how supermassive black holes form or grow. We've only just begun to detect gravitational waves from black hole mergers. The Event Horizon Telescope is still refining its techniques, improving its resolution, observing more black holes. We're in the middle of the story, not at the end. And that's exciting. That means there are discoveries yet to come, insights waiting to be found, perhaps revolutions in our understanding comparable to what Einstein did with general relativity or what Hawking did with black hole thermodynamics. The next generation of scientists will tackle these problems with new tools, new ideas, new perspectives. They'll stand on the shoulders of those who came before and see further, as Newton said, and they'll pass on what they learn to the generation after that. So when I think about black holes, I think about all of this, the physics and the mathematics, yes, the observations and the experiments, definitely, but also the human endeavor, the collective effort to understand, the sense of wonder and curiosity that drives us to ask questions even when the answers are difficult, even when they challenge everything we thought we knew. Black holes are a testament to the power of human reason and imagination, to our ability to comprehend things that seem incomprehensible, to find patterns and meaning in the cosmos. They're also a reminder of our limits, of how much we still don't know, of how the universe is vastly larger and stranger than our everyday experience suggests. And that's okay. In fact, that's better than okay. That means there's always more to explore, more to discover, more to wonder about. The universe doesn't run out of mysteries just because we solve a few of them. It keeps revealing new layers, new depths, new questions. Black holes are part of that endless mystery, that infinite regress of questions leading to more questions. What are they? We know, sort of. Regions of space-time where gravity is so strong that nothing can escape. How do they form? We know, mostly. From the collapse of massive stars, or from direct collapse of gas clouds, or from mergers of smaller black holes. What happens inside them? We don't know. What happens to information? We don't know. What's the correct theory of quantum gravity? We don't know. The answers we have lead to new questions, and that's how it should be. That's what keeps science alive, vibrant, interesting. So maybe the secret life of black holes is simply this. They're alive in the sense that they're dynamic, evolving, affecting, and being affected by their environments. They're alive in our minds as we think about them, puzzle over them, try to understand them. They're alive in the equations and simulations and observations that represent our best attempts to capture their essence. And they're alive in the sense that they continue to surprise us, to challenge us, to push us to think harder and deeper about the nature of reality. And that, I think, is what makes them so compelling, so endlessly fascinating. Black holes aren't just dead ends where matter goes to disappear. They're gateways to understanding, windows into the deepest principles of physics, provocations that force us to confront what we don't know and to strive to know more. They're part of the universe, yes, but they're also part of us now, part of human knowledge and human culture and the human quest to understand our place in the cosmos. And in the end, that's the story, isn't it? Not just the physics of black holes, though that's important and beautiful and worth understanding for its own sake, but the story of how we came to know about them, how we study them, what they mean to us, the story of curiosity and intellect, and the stubborn insistence that the universe can be understood, that we can figure it out if we work hard enough, think carefully enough, observe closely enough. Black holes are part of that story, a major chapter, and the story's still being written. There are discoveries yet to come, insights waiting to be found, and that's something to look forward to, something to be excited about. The secret life of black holes continues, and we're here to witness it, to study it, to try to understand it. And that's a privilege, a remarkable thing, a source of wonder that never quite fades no matter how much we learn.